All right, let's take a look at some problems here. Now, the thing about the binomial distribution is you might wonder what its worth is, because really, are we interested in calculating probabilities for flipping coins and rolling dice? And the answer is not really, unless you're into the casino business. But what we are interested in is studying people. And so think back to the Elvis example here. And so in the Elvis example, we had, let me just go back there to whatever page that was. It was about page 10 or something. There we go. In the Elvis example here, this is what we had. We asked 1,024 Canadians, do you believe that Elvis is alive? And the answer to that is yes or no. And so that makes that then a candidate for a binomial problem here. Now, if it's a binomial problem, we would say that, well, the properties of a binomial distribution must hold. And so that means then that each trial is identical. And so in our particular case then, we're talking about n equals 1,024 people. Now you might look at that and say, well, people aren't identical. But in order for this particular problem here, what we do is we say, well, a Canadian is a Canadian. And unless we find out that people of a certain area think differently than the rest, and we would say that we're not measuring people in terms of other factors such as their gender or anything like that, or how old they are, that a Canadian is a Canadian. So we consider them to be n identical trials. In fact, what we find out later here is that Quebecers are a little different from the rest of the country in terms of what they believe. But what we have here then is that we have 1,024 Canadians. It's binomial because you either believe he's alive or he's not. The P is equal to 10%. So 10% believe that the king of rock and roll is alive. And then finally, the fourth condition for a binomial distribution is that they're independent of each other. And what we're saying here is that if you take a sample of 1,024 Canadians across Canada, it's not likely that you're going to run into people that know each other out of that 1,000. So they're not influencing each other. So that's the kind of thing that we're looking at here. And you'll see a very practical example of that when I talk about the Lou Gehrig's disease problem, which I'll actually talk about in class. It's quite interesting how we use the binomial distribution in terms of looking at the causes of disease. So let's get back here to taking a look at some problems. And we were, what page were we on? A little further than that. So we're looking on page B14 here, number 12, and we're asking the question then, an insurance broker believes that for a particular contact, the probability of making a sale is 0.4. Suppose that on any particular day she has 5 contacts. So let's define the binomial symbols n, x, and p. So again, what you might want to do is to pause this, give this a try as we go through each part, and then we'll just pick this up, and I'll assume that you push the pause button when you need to and try it on your own. So in this case then, we would say n is equal to 5. So we've got 5 contacts. P is equal to 0.4, and that's equal to the probability of a sale and that's for each contact. So remember, a sale would be considered to be a success. The values of x take on the values of 0, 1, 2, 3, 4, and 5. So that's what we've got there. Let's just go back and take a look at the binomial properties here. So I'm going to go way back here and take a look at right in here. So back to page B4, the properties of a binomial experiment. And it says that the experiment consists of n identical trials. So in this particular case, then, we would say that each sale, each person, would be considered to be identical, that there's nothing distinguishing between them that would cause us to think that they would be, one would be more likely to make a sale, you'd make a sale to, versus another one. Each trial has two possible outcomes, and we know that that's true in this case. In fact, as I mentioned, that's the real defining thing of a binomial experiment. In this case, you either make the sale or you don't, so success or failure. The probability of success, P, is the same for each trial, so that is 0.4. And then each trial is independent of the others. We have to make an assumption in this particular case on that they don't know each other, so they're not affecting each other in any sort of way. Let's go back here to the page that we were on here, which is about page 148, I think. Right there. Okay. Construct a table of probabilities. So we're going to have x and then p of x. And I'm going to do this two ways. Do it by hand and also using the tables. So the values of x are 0, 1, 2, 3, 4, and 5. What we're going to do is we're going to go back to page P9 here, right there. And in this case then, we're taking a look at n is equal to 5, p is equal to 0.4. So here's our probabilities right here, these guys right there. And they correspond to the x's over here. All right? So we're just going to transfer those over to the next page here then. So let's go back to where we were. And so that first one there was 0.0778 and then 0.2592. And these just came from the table. 0.3456, 0.2304, 0.0768, and 0.0102. If you add all these up, they have to add up to 1, or 100%. All right, and then we're going to calculate probably just a couple of these by hand. I'll leave the rest for you. So let's do, say, the probability that x is equal to 0. That's going to be equal to, remember our generic formula is n choose x times p to the x times 1 minus p to the n minus x. And so that's going to be equal to 5 choose 0 times 0.4 to the 0 power times 0.6 to the 5th power. And that will be equal to, well, 5 choose 0 is just 1, right? That's 5 factorial over 0 factorial, 5 factorial. And 0 factorial is just equal to 1, and then the 5 factorials cross out. So 1. 0.4 to the 0 power, anything to the 0 power is 1, and then 0.6 to the 5th power is 0.0778. And so that's where we get that first number then from. Let's do one more. Let's do the probability that x is equal to 2. So that will be 5 choose 2 times 0.4 squared times 0.6 to the 3rd power. And that turns out to be 10. And that's just 10 factorial over 2 factorial, 3 factorial. You can figure that out to be 10. Times 0.2 squared, which is 0.16. And then 0.6 cubed is 0.216. And that turns out to be 0.345. 5, 6, which is the probability for x is equal to 2. So you could do that for all of those. In fact, I suggest that you do, and then if you run into any problems, then we can take those up in class, or you can ask me separately. But you, of course, have all the answers. They're all right here. Draw a histogram of the probabilities. So in this case, then, we're going to start here with a, let's do this. So this is going to be the p of x's. This will be the x's, and the possible values are 0, 1, 2, 3, 4, and 5. Those aren't exactly spaced out right, but... And then, what was the highest one? It was about 35%, right? So let's go up by 0.05s. 1, 2, 3, 4, 5, 6, 7. So 0.05, 0.10, 0.15, 0.20, 0.25, 0.30, 0.35. And so what we've got here then is, let me just make this a little smaller so I can see them. 0.0778 is just going to be, it's actually just a vertical line, and it goes up to about 0.008. And then for 1, it goes up to about 26%, so up to about there. Well, I didn't take, did it? Okay, let's try it again. Like that. And then for 2, we've got about 35%, so, ooh, that's a terrible line. Doesn't recognize that as a line. Let's try it again. There we go. And then for 3, it's about 23%, so just about as high as this guy here. And then for 4, it's about like that. Oops. And then just a little guy here. So that's what your histogram looks like for the probabilities, just like that. Remember, there's nothing actually in between each of these. You get 0 or 1 or 2. You can't get 2.5 successes. What's the probability that she makes 3 or more sales in a given day? That would be the probability that x is greater than or equal to 3. So that's the probability of getting 3 or 4 or 5. Okay. And so all we do then is we just go up here and we add these guys up. Oops, I guess I could just use these. So we just add these guys up here. So that's going to be equal to 0.2304 plus 0.0768 plus 0.0102. And when the smoke clears, you get about 32%. So there's a 32% chance that she'll make 3 or more sales on a given day. How many sales should she expect to have in 60 days? Now here's the word expect. And whenever you see the word expect with a probability distribution, we're talking expected value. Expected value is the mean. The mean is equal to n times p. So that's going to be equal to 5 times 0.4 is equal to 2 per day times 60 days is equal to 120. We're going to assume here that this is a big enough area that she actually has 120 people or sorry, I guess that would be 5 times 60. That'd be 300 people that they don't have any contact with each other, and so it's large enough that we actually have a sample of 300 and that they're independent of each other. So it would turn out to be 120 if this were binomial in nature. All right, I'm going to leave you with this problem, and we're going to take this up in class. A couple is planning to have 8 children. That's going to be your n, not all at once. They're interested in determining the probability that they have exactly 3 girls. Define the binomial symbols here and state any assumptions that are necessary. The thing to note about here is what's the probability of having a girl? And that turns out to be 0.5. So that's the probability of having a girl. And then here's your n, 8 children. And so you can fill in the rest here. And we will take that up in class. By the way, before we leave this one, why is it that the probability of having a girl is 0.5? And it's erroneous to think, and this goes back to our very first lesson here on the binomial distribution, it's erroneous to think that it's just because there's 2 possibilities, a boy and a girl. That's actually erroneous. The reason is because worldwide we actually know that the numbers are from the World Health Organization and from other censuses and so on like that, that they're almost exactly 0.5. In some countries it's a little more, in some it's a little less, but worldwide it's about 50% boys and 50% girls. So that's what happens. That's why it is, not because there's 2 possibilities. Again, we could talk about, are we going to have a tornado tomorrow? And the probability of having a tornado would be really, really small, close to 0. And the probability of not having one would be very, very high, close to 1. All right, I'm going to leave you with that problem to work through, and I will end the video here.